All right then. So we haven't quite finished with the last lecture, and it was about calculating integrals. Okay, let's briefly begin with this exercise, which hopefully, if you came to the last lecture, will be simple enough. I want you to use Riemann sums, or whatever we learned for integration, to figure out what's the integral from 0 to 2 of x squared dx, and try to at least set it up as fast as you can, and then calculate. And the hint, guy, is that you look at it, it's very, very clear what's happening. Here we are summing up all the areas of rectangles. Altitude of those rectangles is always x squared dx. So x squared is the altitude at the point x times dx is the area. And the rectangles are built from 0 to 2. Okay? So set it up as a Riemann sum and see how fast it will take you, right? And then we'll calculate it from there.
You want the limit?
Yes, set it up as a limit, and
Well, a lot of steps.
well, once you're comfortable, it takes very few steps. It's almost immediate. Hello, David.
Hello.
Yeah, it happened twice. There is this yellow box appearing here. I have no idea what causes it. So they say remove something from screen. What window? Whatever. Okay, guys. So again, as complicated as those concepts might appear, truly there is nothing more here than just adding up a bunch of rectangles. If you can see that, then a lot of the theory becomes already predictable ahead of time before I ever say anything about it. So Sam, thank you for your input. I think there must be some small error that you are making. One thing is that 2 over n times 2 over n squared, that is only part of what appears there, right? You are missing an important part there, because the limit of this expression is 0. And the area under this curve, obviously, it's a parabola. It will not be 0. All right, so since we do have quite a few things to go through, let's do it now together. So you see, I personally, again, I imagine the Isle of Manhattan, but one-dimensional version of it. So it's an interval from 0 to 2. And over this isle, we are going to construct a skyline, a bunch of very thin skyscrapers. And how do we construct them? Why do I use Manhattan as an analogy? Because the skyscrapers are very thick by one other. So, sorry. Well, you understood what I'm trying to say, yes? So the skyscrapers are stuck one next to the other. It's because I was doing something regarding German, so I'm just in another mode. So what happens here is we start at 0, right? So how do we construct? So my suggestion is to use the right-hand rule, the right-hand approximation. So first of all, you take this interval and you want to construct a very large number of skyscrapers. Each of them are going to have the same block thickness, right? So the same city block. So what you do is you divide this interval by n. So the thickness delta xn is 2 divided by n. Good? 2 divided by n. And we are going to construct the elevations at the point xk. So what we do is I decide to begin at 0 and construct from left to right. So I'll construct first height. So how do I construct the kf height? Hello, Sarah. How are you doing? If you're feeling good, I will be happy to see your face.
I'm good. How are you?
All right. So what we have is the point xk is, I think I had pictures of it somewhere above. Yes, you see, this is the blueprint of the construction. So I begin, let's say, at the left point. And then why do I use the letter R? Because the elevation is constructed at the right point of the interval. So I move to the right, construct elevation. Move to the right.
You're making a right-hand approximation?
Yes, I'm making a Riemann approximation, right? And then I take the limit, and in the limit, the rectangles are going to be just exactly fitting under the curve. So that's the scheme, okay? So I need the point xk. So notice that for all of them, let's say to get to the construction site k, this construction site, I need to displace from A, that means A plus, displace from A by k blocks. And then you arrive here, right? So displaced by 3 blocks from A. So 1 block, 2 blocks, 3 blocks, you arrive at this point, and that's the point x3, which is given like this: A plus 3 delta xn, which is A plus 3 b minus A over n. So your goal, if you can, once you get it, your goal is right away to see this formula and to recognize it, right? So the right-hand rule is it reduces to this Riemann sum. You see it? So K1, it's first block all the way to the last block. This is the construction of the elevation, and this is the thickness of the block. So maybe the summation looks complicated or foreign because it's like a new language here.
Professor, yeah. Can I say what it is for our example?
Go ahead. What is that for our example?
Is it going to be for the Riemann approximation? We're going to have sigma, we're going to have n and k equals 1. Hold on. Is it going to be k times 2 over n? Just k times 2 over n squared?
That's the elevation, correct. K times 2 over n squared is the elevation at the kth point, correct, right? So we have f of xk, it's k times 2 over n squared. And then to complete and make it an area, you multiply by 2 over n.
Why?
Make sense? Because this is just the elevation.
I got it.
It's
okay.
It's a height times width. So this is just the height.
Geometry.
Yes, just geometry. So this is the pattern that you see, guys. You understand what you're doing? Nothing fancy. You're just adding the areas of lots of rectangles. The only difficulty is that there are many of them. It's not 1, 2. There might be millions of them, right? So that's what you're doing. So what you have in sum, you see where the mistake comes. you wrote 2 over n times 2 over n squared, but really it should be k times 2 over n squared times 2 over n, where k goes from 1 to n. And that's the Riemann sum. Okay. If I had to type it here, I would have written
No, I
something.
wrote this. I wrote that, but I didn't write at the end. There's a 2 over n because of the height. I forgot about that.
You know, but that was sums, right? So somebody else. So it's k1 to n of. You don't even need to write off. You can write simply k times 2 over n of that squared.
Times 2 over n.
Right, times 2 divided by n, right? And you see, so you can write, if you want to text me how it is, you can write something like this. I would understand.
Yeah, that's okay.
Okay? Because the summation is kind of not important. What's important is the step from 1 to n. Good?
I got it.
And then it's very fast for this example. So then what you do is you want to get rid of anything in the summation that does not involve k, because k is really updating by the sum. So then I have 2 over n squared times 2 over n, which is 2 over n cubed, 2 over n cubed, which I factor out. And I now have a sum from 1 to n of k squared. And we know how to deal with the sum, correct, guys?
Right. Hold on a second.
Yeah.
I continue. Sorry.
Yeah. So then what? Then we already from above we developed a formula for how to sum this, right? So the closed form of the summation is simply n times n plus 1 times n plus 1 over over 6, right? So basically of this expression and times 2 over n. And then I need to take limit as n goes to infinity. So I'm back into the beginning of the semester where we took limits at infinity. And if you learn how to do that very fast, you can look at this expression and see the answer without doing anything, doing any algebra. So look at it. What do I pay attention to? I pay attention to the leading term on the numerator, which is 2 cubed times n times n times 2n. You see? So it's 2 cubed times 2n cubed. So altogether, what we will get, and then the denominator, it's 6n cubed. You see? So those are the only things that matter when I take limit to infinity, the box method, or thinking inside of the box, as I call it. So,
wait, Professor, can you restate that one more time? That whole thing you just said?
yes. So which part? So here.
No, down. When you're talking about the limit.
Yes, when I talk about the limit, remember from way back at the beginning of the semester, what we have is the limit at infinity of ratios of two polynomials or of a rational function is completely determined by the leading terms. The leading number, to the leading power of n together with its coefficient divided on the bottom by the leading power of n together with the coefficient.
Oh yeah, so it's simple at this point because n is striving to be such a large number.
Right.
Okay.
So we have if you look over here, be careful. It's not n cubed. It's n times 2n. That will give us the biggest term here. So it's 2n cubed here. So I only look at this part, at that part, and at the 2 cubed. That's my numerator, and my denominator is 6 with the n cubed. So then the n cubes can be cancelled, and I see this. I see 2 cubed times 2 over 6. This 2 came from here, and then pretty much then the answer is 8 over 3. Good.
Yeah. Simple.
Okay, so there are going to be more Riemann sums, but I will move on. So when you practice, you can open this lecture note and don't look at the solution. See if you can get the solution without my help, right? Just see that you can do it fast, and then you look at what I wrote over here. You understand?
How long are you giving us?
No, right now I'm going on. I want to talk about other things since the semester is short.
Oh, so you want us to do this on our own and text you privately?
Yeah, this is solution is available here, right? So there are a few of them where solution is available.
Oh, okay.
So if you want to write it before, so you want to look at the notes, let's do this, guys. Right?
Yeah,
Write what you see over here, and I'll show you the next one in a moment. Then after the lecture is over, when you're alone, you try to calculate this integral and see if you can do it.
Okay.
Okay. You have this one, yes?
Mm-hmm.
Yes, you copied. So, and also copy this one here. Okay. So they get a little bit more complicated. It serves two things. First of all, when you do that, you start seeing the pattern faster. You can do the calculation very fast. Although soon we are going to find tricks. They're going to be in next lecture. We are going to learn that you can just do it very, very fast. Still, it does not eliminate the need for Riemann sums, because that's how those integrals appear to begin with, right? In other words, when you're dealing with all sorts of problems, when you're trying to create a theory or describe something, you end up with some summation, which you then recognize that you can convert to this form. Okay, so you copy this as well. And then here is another one, right? There are three here that I would like you to do on your own, which we can afterwards discuss together, or you do it at home. I mean, and then look at the solution, okay? You copied this, everything copied, this one copied, wonderful. So here is what I want to say now, next. So you understand what we're doing. Again, we have a curve, and under those curves, we have those thin columns, and there are many of them. And those thin columns, their areas are supposed to represent a very good approximation to the area under the curve. And that's why we take the limit as it goes to infinity. Once we make them thinner and thinner and thinner, then you get more and more of them, and they fit hopefully better and better under the curve. And then the approximation gets better and better, becoming perfect in the limit. Yes, guys? So let's say, yes, Zina. Yes, Alexandra. Yes, Zina, good. So you understood, right, guys? Yes, wonderful. And guys, do not hesitate to show me your faces. I know I'm strange. I suppose some people say I am. And maybe scary, but, you know, I do like to see you, so I can gauge your reaction. So this is what I want to say next. You see, so the idea of this picture is, look at it. By convenience, I constructed elevation at the rightmost point. But there is no need to do that, right? It seems that if my curve is continuous, if this column is very thin, by continuity, the elevations within this interval are all essentially the same. I mean, I drew it exaggeratedly curved, but the elevations are essentially all the same, correct? And that means that in general, I am free to, for continuous function, to define the integral from a to b of f of x dx to be the limit as n goes to infinity of gn, where g stands for general rectangle. In other words, you see, you can take this xk star to be any point between the left and the right point at which you construct the rectangle, okay? This is not necessarily useful in calculation purposes. This is useful for sure in understanding how those integrals are formed and recognizing, okay? Which you will see hopefully already today. I have quite a long lecture after this one where those ideas are used, okay? So you understand? So in general, the procedure is to divide the interval from AB into many segments. They, by the way, also do not have to be of the same size, but I don't want to go there. We don't need it for our class. But for our class, we are constructing them as uniform blocks. So we're kind of doing Manhattan type of construction. Every block is the same, and it's one-dimensional Manhattan. You can do two-dimensional Manhattan or higher, right? But every block is of the same thickness, but the skyscraper over that block is not of the same height. And if the blocks are very, very thin, doesn't matter where you decide to create the elevation, here, right or left point, or in general, okay? That's why G is here. So here is an exercise that I would like you to figure out. So here is an integral. So you're constructing a city whose elevation, whose skyline is f of x, okay? That's the skyline of the city. I want you to express this integral as a limit ln, where you can figure out what L refers to, right? It is the left endpoint. So in other words, for each rectangle, for each, sub-interval, I am using the leftmost point of that interval to create my elevation there, okay? So xk, the point, this point, is always at the left corner of each interval. So take a little bit, a few minutes. Let's say I will give you 3 minutes, okay? And write to me, what is this thing? Formula.
For ln?
Yes, do you understand? L sub n means left and left construction, right? So we just add Rn, and that's my notation. I'm not sure what others use. The point is I'm using the left point, right? So for this interval, Rn means that I use this edge, and for Ln, it means that I use this edge. Make sense?
Yeah.
Cool. So if so, I want you to describe this procedure. like I did for Rn.
Professor, I'll be right back.
Sure. Well then, I guess we're ready, correct? So here is how you go about it. So this is the scheme of our construction, understand? So for first rectangle, I'm constructing elevation at A, for second rectangle at x1, for third at x2, etc. So I just need to describe how the workers should move to their construction position, okay? So the KF construction is happening over here, okay? How do I move to the KF construction? You see, if you can kind of skip over it, if not, just go through each step until you see the pattern. But here, look at it. To go to the KF construction site, I don't want to walk K blocks. How many blocks I want to go? K minus 1 blocks, right? So for example, to get to construction site 2 is here, right? So I displace only 1 block. So it is A plus K minus 1, B minus A over N is the length of a block. So it means start here and walk to the right. That's how I describe this integral. That's my scheme. Good? So guys, when I say, so this is, okay, it's good if it should remind, I'm not sure about cache memory block. I do not know enough, I'm old. What do I know about computers? But it's nice when it reminds you of many things. It does remind me of it. Integration reminds me of my friend or my conflict with friends or some. I have a lecture about it for probability. So what happens here is then it's this, right? So this is the movement to the cave construction site. So that means I displace by K minus 1 blocks, and I arrive here and I construct the elevation. I plug this point into my function. Okay, so that is what ln is. It's the summation where K goes from 1 to n. That refers to the block, first block all the way to the end block, and the elevation is constructed at the left point of the block. which is a plus k minus 1, b minus a over n, times b minus a over n. And I think it's much more convenient to just notice that, okay, first block displays 0, second block displays 1. So in other words, more convenient is to write summation by just changing the k. So it's k equals 0 to n minus 1 of f a plus k b minus a over n times b minus a over n. Make sense? So here I haven't changed anything about the function. I just changed the bound of summation. It's expressing exactly the same thing, because when k is 1, this is 0. When k is 2, this is 1. You understand? So I prefer this version of it. Okay, good. They are, of course, they mean exactly the same thing. So in this version, the difference between right-hand sum and left-hand sum is that right-hand sum will start from 1 to n, and left starts from 0 to n minus 1. And this is the form for it. Okay. So I will, in the next lecture, explain why you need all those variations. You have to recognize all those variations and see what sort of thing it is. Here is another problem, guys. Now I want you to express Rn, but this time I want you to move right to left. You understand? So in this scheme, I move from left to right. But why not start at B and construct the rectangles this way? Like in Hebrew, right? You write from what? From right to left.
Left to right to left.
Whatever. I told you, left and right are confusing me. I lose orientation. But you write from this side to that side, apparently, right? So do that. Do this construction. Yes, guys. Again, it is rather sensory depriving, or it's a sensory deprivation to not see your faces, to see your beautiful young expressions, eyes full of thought. Oh, Sam, I see the Golden Gate Bridge and you as a ghost in it. Hmm. Nice to see you, Sam. Guys, of course, guys, I don't want to make you uncomfortable or invade your room, but when you are around, it's very nice to see you.
Was that supposed to like help us figure out what to do?
Yes.
Oh,
I
was
mean,
it?
I'm not good at walking on air, but yes, right?
Okay.
You're a construction worker and you start at B. then your first block is here,
Right.
right? The next block, well, you decide if it's right hand. The first block is actually at B. That's the right hand point. You build the
Right.
block here. So yeah, it's like this. You see, guys, that's what I see. A construction site
I also see
and
that.
a city is built. So it's very fast then.
Okay.
Is it like super simple or?
Well, I don't know. I mean, it depends on what you're used to, right? So people say it's like riding the bicycle, right? But I learned to ride the bicycle at 18, and I did it at night, so that nobody sees the shame. And every time I ride it, I break my leg. So you see, right? So it's not that simple to me. All right, so let's do it, guys. You have to visualize. You see, this is the scheme, correct? That's the scheme of construction, right? And so what else is there? All you have to do is tell the worker how to get to the KF position, okay? So first position is here, right? First position is here, second position is here, and onwards, right? So what happens then? So to build the first position from B, you want to displace by how much? First construction, don't displace. So that means you displace by 1 minus 1 of the interval, right? And in general, I wrote it like this, right? So in general, you move to the left. So it's B minus how much to displace. So xk is B minus k, B minus a over n, where k is from 0 to n minus 1. Do you see this formula? I see right away the general case, but here is how you can look at it. What's the rule? I'm constructing an elevation at the right end point, so at here, at this place, right? So that means I start at B. First, don't displace. This is the size of the block. B minus because you move to the left, right? So B minus 0 times B minus a over n. So that will construct elevation at this point, right? Then the second point is here. So it will be B minus 2. B minus 1, I'm sorry, because for this construction, this is where the elevation is, you see? Because I'm using right-hand point, you understand? Right-hand rule. So so then I see that the pattern is simply that xk is B minus k times B minus a over n, where k goes from 0 to n minus 1. So then Rn looks like the left rule. Looks like the left rule, but starting at B, and there is a negative here. Do you see that? I need, guys, some sort of verification whether you understood, or should I go again and explain something here? What you see, what do I see here? Something very simple. I construct rectangles, and how do I do that? I plug the particular construction point into the function to create the elevation, and I multiply by the width of the block, and I add over all the blocks. So it's very simple then.
Yeah.
Good.
I'm good. I don't know about everyone else. I'm fine.
Yeah, I'm also.
Okay, good, right? So if you are that good, what about describing to me Ln, but starting at the point B, which is not written in my notes. So I want to see either text or some sort of thing here, right? You understand how to input it. So for example, this summation I would have written as k equals 0 to n minus 1, and then simply f of B minus k, B minus a over n times B minus a over n. That would be how I would have submitted the solution if I had to text it.
Okay.
Okay. So you are able to text me the solution if you want to, or I guess push it to the screen. Maybe I can see it.
So what are you asking exactly?
I want the formula for. I want this. I want the area of the under the curve f from A to B, but where the construction starts at B, and where you are using the left-hand rule. In other words, where the elevation is constructed always on the left part of the interval, like this, right? So, but in here I started construction from this point and move to the right. Now I want to start construction from this point and move to the left.
Okay.
Okay, right. So I want ln expressed yeah, express this limit, but starting at b. Maybe I did put it in the notes.
So from B to A?
From B to A, yes. You move from right to left.
Okay.
Yihuan, why are you so silent today?
What?
Oh, good. Good response. Oh, it's nice. I hear you. But I don't see you. And you, Melissa? Oh, Alex. Wonderful. It's
Professor-
very interesting, yes. So what sort of thing am I looking at, Alexa? It's like half of your screen. That's cool.
Yeah, I have my webcam underneath my plugin webcam turned
Okay.
on, so I need to adjust it.
All right.
Professor, isn't it, do you take,
Yeah, so yes, so type the solution. I will look at it and I will be able to judge.
Professor, is it the sum of 1 to n plus 1?
I don't know. Why from 1 to n plus 1? Depends how you so how do you set it up? You see, you can make bottom number and top number anything you like. It depends. It's the full expression.
I understand. Okay.
Right. There are some ways I prefer it, but it could be from 1 to n plus 1. It depends what's in between. All right, so as we have to move on. Oh, okay, wonderful. Somebody wrote Sam. Okay, 1 to n. But you started with A. I think there is a typo. You probably mean F. Could you correct some? Is it F of B?
Professor, isn't it just interchanging A and B?
It's very simple to that. Yes, it's like interchanging A and B, but not everywhere. So Sam, just look at your answer and tell me, do you mean F of B minus, or you don't mean A here, or do you?
I didn't mean A, but I think it's wrong.
Yes. So what you wrote would have been correct, but you wrote A. It should have been B. So right. So what it should be is from k equal 1 to n. We look at it. You can see it over here. K equal 1. You displace 1 unit all the way to displacing all of the units from B. Then that would get you to A, because you're using the left hand rule, right? But you're moving this way. So that means it's like the right hand rule, but in reverse, right? So it will be k equal 1 to n. That would be how I would say it. Yes.
Can I didn't look at his answer, but can I give it a go?
Okay, well, I'm not sure. What do you want to say?
can I give it a go, like what it might be? Because I didn't look at his answer.
But we have to move on. Let's do.
Okay, fine, fine.
Let's
Right.
talk
Sorry. Go
about that.
for it.
So,
Go for it. I'll just tell you if I did it right or not.
all right, all right. So basically, you move to the left, which means you start at B, and then to get to the cave point, you need to displace from B to the left K units, right? So it would be B minus K times B minus A over N, which is the length of the displacement, and you plug the entire thing into F. You can see the text. Look at that. Open the text. You should see it, right? Multiplied by B minus A over N. Don't worry. You have one more question, which is actually, I'm not sure if you'll find it hard. Right? I don't also have too much time to spend on it. Okay, Alex. So here is the next challenge. Let's see if you can do that one. I want you to express the integral using midpoint. You understand what's a midpoint? It means the point in the middle. So the point in the middle of the interval is used to create elevation. Let's see if you can do that. You understand? So what you're now asked to construct is you have a skyline, which is represented by f of x, and you want to find the area below that skyline from A to B. You can start, let's say, at A, it doesn't matter, right? Start at A, go to B, move from left to right. But the elevation is to be created in the middle, in the center of each interval. You understand why the limit of mn will be this integral? Because if the function is continuous, it does not matter, as I said before, where you select the elevation in each interval. Because when those are very, very thin, the elevations over the entire interval become almost identical. They become almost the same as here, or anywhere in between, if the function is continuous. So they are not the same for small n, but once m is very large, there is very little difference between the summations. It's like in that picture here. Okay, so if it's once the intervals are very thin, any elevation in this interval, not like even this picture, it's going to be almost the same.
All right.
You see, Sam, you write k over 2, but k over 2 is not always an integer. No, actually, I see what you're saying. Be careful, because sometimes it's not in the middle, right? So you have to reconsider what's happening here. For example, Sam, if you set k equal to 2, right? From 1 to n, 2 will appear. So k equal to 2, you displace by one entire interval, and you don't get into the middle of the interval there. Do you understand what I'm saying, Sam? So,
Yes.
for example, when you start here, your first instance is 1/2, so you do get here. You decided to start from the right and move left. So then, first instance, you're here. But next step, you're here, and that's not the midpoint.
Yeah.
I'm kind of confused. What are you asking exactly for us to do?
Well, you can try to phrase it in the previous questions. Were you confused? Left-hand rule, right-hand rule. What all this is describing, is how the rectangles are constructed, right? So what you need to have is to divide the interval into n parts, and in each part you have to decide where to build elevation, at which point to construct the height of your rectangle.
I understand.
Right. So we decided to do it on the left point once. We decided to use always the right point, and M means decide to use the midpoint. And I want a formula involving the midpoint. So in other words, to describe the summation, where what you do is you move to the center of the interval, create the elevation, then move to the center of the interval, create elevation. So in each, it would be like this picture, but the arrows will be coming out of the middle of the interval. You see here, the arrows are coming at the right point of the interval. For this interval, the upper arrow is at the right edge of the interval. This is at the right edge of the interval. This is at the right edge of the interval. I want a construction where it's coming from the middle of the interval. Make sense?
Yep.
Cool. So,
Professor, I think I have to leave early today.
all right.
But is there a time I could call you?
Well, you can try after class, I guess, or tomorrow.
Okay, I'll try tomorrow. Is there like a better time?
I don't know. I mean, the way it works, you can try to contact me, and if I'm picking up, then I'm contacting. If I'm not picking up, it's basically, yeah. If I pick up, that means it's fine.
Okay, fine. We'll talk.
Sure. The number of things that you add is always the same because you have n rectangles, so there will be n rectangles. So a plus b over 2 is not, a plus b over 2 will be just one number. This does not have to be an integer. This does not have to be an integer. So be careful, Alexa, right? So when you say array, right? So this is not an integer necessarily. This is not an integer. So a plus b over 2 does not have to correspond to an integer at all. All right, let's do it together, I suppose. Here is how you can think of it. Here you want to create the construction in the middle, right? So what is middle? Middle is the average of the left point and the right point. Okay, maybe, well, that's what you, Alexa, wanted to say, perhaps, right? No, not quite, but I think maybe this point plus that point divided by 2 is the midpoint. Yes, I think so. So what you have is xk star. That's the point at which you construct elevation. It's here. It's the average of those points. And I already know how to describe the left point and how to describe the right point, right? Because xk is a plus k b minus a over n. That's how I get to this point in terms of the interval. And xk minus 1 is a plus k minus 1 times b minus a over n. You see that?
Yeah.
And then I add those numbers and I average. Now once I add those numbers, a plus a divided by 2 is just a. And then I take the second factor out, so it's k plus k minus 1. So that will be 2k minus 1 divided by 2 times b minus a over n.
Can you scroll down more? I can't see.
Yes.
Thanks.
Good.
Oh, wow.
So,
Okay.
yeah, so you understand, all I did is just average those points.
This is for the midpoint, yeah?
This is for the midpoint.
That makes a lot more sense.
Okay.
I wasn't paying attention fully. I'm sorry.
No worries. So next is another challenge. Okay, so now I want you to identify from the Riemann sum, identify the integral. So you look at it and you say what is being constructed. So you need to be able, and I will show you possibly below what it is. So you see, you look at those questions. Okay, you don't need to solve anything. I just want you to look at it and tell me, what do those Riemann sums represent? What integration is happening? In other words, what's the function? You have to put it in this form, okay? It's a sum from A to B, so you need to know what's A, what's B from this expression, and of what function. Good? Can you do that? You understand? One major thing about it, so if your ability to recognize in Calc 1 is good, then all those problems are kind of, they are the same problems. Then. If not, then it's like every single problem is a different one. Beautiful sum. That's the function. If you could, so solution is something like this. I want you to say A equal B equal, and then F equal. Okay? You understand? So I need to know what's the lower number, what's the upper number, and what's the function. And this, I mean, then I can complete. I know it's integral. I know there's always a dx there or something, right? So you identified the function marvelously, right? So it's correct sum. But
That's
what are the?
what your cursor is on is f of x of k.
This exactly. This is xk.
And on the right, you have the change in x. That's the height. That's the height. No.
So the height at the point xk is this.
Okay.
And the width is, you can see it over here, right? That's the width.
Which is the change of, well, which is how do I word it again?
It's the thickness of a block. If you divide the full block into n segments, this makes the thickness of that block.
Different word that I remember. Okay, give me a minute.
All right. Oh, Melissa, A equals to. There are several possibilities, but if you agree with some, if you decide it's x squared plus 1, then A equal 1 and B equal to 3 is incorrect.
Say again?
No, and Sam said, so A1, no, Sam. You all identified, Sam identified the function x squared plus 1. Okay? If it's, there are several functions that would work correctly, and then there are different bounds of integration. But if you decide that it's Sam's function x squared plus 1, then the bounds of integration are determined as well. I will explain in a moment how to do that, but I want to see if you can right away see it before I explain. And great to hear, Melissa. It's just too bad I don't see you or don't hear you. And David, you too. Where is David? David is silent.
Yeah, I'm here.
Yes, there you go, right? I don't see you or hear from you.
Yeah.
All right, so since again it's already 7 and I want to cover the next batch of lecture notes, let me show you how to do this, okay? So first of all, this is the thickness of an interval, right? So if I eliminate the n, I already know that the full interval is of length 2, right? Because b minus a divided by n would have been this number. B minus a, right, is the length of the interval. So b minus a apparently is 2. So I know that the length of the full interval is 2 from here, okay? So this is how I solve it, okay? So here, where you see the k, that's my xk, okay? This whole thing is f of xk. This is my delta xn, okay? So if this is xk, what do I see? I see that I begin at 3 and I move plus to the right by those increments, right? So setting k equals 0 gives me the lowest bound, 3. If k is equal to 0, you see, I look at it, I can already retrace where...
If k is equal to 0, then a is equal to 3.
Right, because I see it's plus means, let's say this is a positive number, so I start moving from 3. When I construct the xk, I move from 3 to the right. right? So that means that if k equal to 0, I see what's the starting point. Where do I begin displacing from? And that is the number 3. Now, how do I figure out where I end? What's my my end of the project? The last point, B, of the interval. Can you see
Well,
it?
then you want to set k equal to n.
Precisely, brilliant, right? Because you displace by all the segments to get to the last point. So then you see the last point is 3
Can I ask
plus
a question?
2. Go ahead.
So if since in this case, is it going to be just, isn't it not be is also like, is it not going to be that the endpoint is also going to be equal to 3?
No, but you just said yourself, you said k equal to n, but there is 2 over n. N
Oh,
means
okay,
that
so
you
then
display.
it's going to be 3 plus 2.
Yes.
Okay.
3 plus 2 is 5, exactly, right? So this is the beginning of your displacement, and 3 plus 2 is the end of the displacement. If you set k equal to n, you can see the end of the displacement. You understand why do I see this? Because I very clearly see what's happening here. I think a person begins to construct this skyscraper. He begins at 3 and displaces to the right. So this looks like the right-hand rule, right? Rn, because I start from the point 3 and I displace to the right, creating the elevation at the rightmost point.
I
So
feel
it's
like an
3 plus.
architect.
Exactly. That's or I usually feel like I'm just observing it. I'm passing by and I see, oh, the person started work from 3, and by the time you get to the last block, to the nth block, that would be n intervals that have to be displaced. So it's 3 plus n times 2 over n, which is just 3 plus 2. All right. So so that's how I get it. Okay. If you understand this, here is your next challenge, B. I want you to do it very fast. So B.
Wait, Professor, what are the, okay, so since we have two, aren't those 2 points of length?
Sorry.
Since you see -1 plus k, 4 over n squared plus 5, the middle term, the x of k, I'm trying to ask, like, isn't that just finding 2 points of height, if I'm correct, or am I not?
Well, I'm not sure about the point. It's if you look at it, you see a function. What was the point at which the elevation was constructed, right? So this is just telling you how the elevation was calculated once you know where to build it. So you need to know what's your point xk, where it is, right? And where you begin and where you end.
I understand. Okay.
Okay.
Yeah.
So, and do it fast, guys, because I do have to move to the next lecture.
So it's not, this isn't that crazy. In the end of the day,
No, it should not be
you're gonna
crazy.
want to put f of x is going to be equal. You're going to set all of the inclusive terms. You're going to get x squared plus 5. Yeah, you wrote it. Good. Sam got it.
Okay, so yes, Sam, right? So it's and then x squared plus 5x plus 7. Brilliant, Sam.
So then when you set k equal to 0,
Yes.
you're going to get, give me a second. Oh, did he already say it?
Yeah, I did.
Oh, okay.
Sam wrote the answer, right?
Sam
yes.
took the floor.
Yes. So here I'm again showing you guys. Guys, if you're confused, also don't forget where you can talk to me even after class and whatnot, right? And also during class. So don't be too stressed about anything. No point to it, right? So here is my diagram, okay? So I look at it. This is my point xk clearly, right? I see that construction started from -1 and I was moving to the right? So since k starts from 1 to n, I see I was using the right-hand rule, right? The Rn, right? So right point construction. So then I see what happens to xk. It was squared 5 times this point plus 7. So the function is x squared plus 5x plus 7. Xk is this thing. And then I can see the bounds. If I put k equal to 0, I get -1. If I put k equal n, I get -1 plus 4, which is 3. So my integral is from -1 to 3 of x squared plus 5x plus 7. Okay, and the last one. No, actually, there are 2 more. What about this one, guys?
This I just did it. Can I tell you what I got?
Okay,
so you're gonna get f of x is equal to the square root of x plus e to the x, right?
Mm-hmm.
And
well, bounds of integration.
Bounds of integration, fine. And then xk is gonna be equal to k plus 1 times 1 over n.
So for the xk I don't want. Just tell me the function. The function you did is what did you say the function is?
Square root of x plus e to the x.
Exactly. Exactly. And what are a and b? Because really you need function in a and b. What are those?
is A going to be, hold on a second. Is A going to be equal to 1 and B is going to be equal to 2?
Yes. So you put k equals 0, it's 1. K equal to n, it's 1 plus 1. So the integral, again, what it is, you see, this is the function.
Yep.
Those are the xk's. And so it's root x plus e to the x. And the first point is 1, second is 2. There are other solutions that are possible, by the way, right? One other solution is integral from 0 to 1, where this would be root of 1 plus x plus e to the power of 1 plus x, right? That would give you the same integral. But simplest is to just take this entire thing as your x, okay? Wonderful. And now last question for this section, and you already, I think you got it more or less. I want to see what other people say. Again, guys, look at this. I wrote it out like this. Tell me what is this expression equal to. It's an integral, right? I just, instead of writing the summation, I just to train your eyes, I wrote it expanded form. So do it quickly, and then I move to the next lecture. And where you hopefully will see where those things, they come together or begin to see that. I want to see what others might say.
I'm just a little confused.
Mm-hmm. So you see, this is e to the power of minus 1 plus 1 times 1 over n times 1 over n. E to the power of minus 1 plus 2 times 1 over n times 1 over n, and onwards.
Yeah, I don't know what to do here.
Do you have videos on it?
What, Batel? Sorry, say it again.
Do you have videos on it? I don't know the answer. Don't get excited.
Oh, videos on what? Of course, I have the other videos on it from previous classes. But again, guys, what are you doing, right? You're just trying to recognize an object, which is kind of very strange how people recognize anything, but they do. If you study what I don't want to kind of to float too much. I might get distracted. I was always almost about to tell you about those experiments that that they did with.
It's not a number, right?
Well, the answer will be a number when you know how to evaluate it. What I asked is to recognize that this limit is an integral. I already told you that, right? So to look at it and say, this thing is this thing. Okay. Okay. So Sam says from 0 to 1 of e to the x, you made a slight mistake. You're right about the e to the x, but you're not right about the bounds. David, the number n is just that n goes to infinity. So right away that tells you the answer cannot involve n. Guys, do you understand that this symbol and this thing is the same thing? What are we doing? We start at this point, at -1. And we begin and construct. Just look at it, 1, 2, all the way to n. That means that that we are moving by this increment, right? 1 over n is the increment that we are moving by. So you see, why are you not able to get the bounds? Because you memorized it like, oh, k0, kn. But that's not what I do in my head. K is just the step. What I'm doing in my head is I ask myself, where is construction beginning, right? The fact that I see 1 over n everywhere here and I see it over here, that tells me that I'm having rectangles of the same width. You see, they're at the same width here. And e is just the function, but what matters is the point x1, x2. You see, you have 1 here. That makes it x1. That makes it x2, and that makes it xn, where I'm pointing it. You see? So now, Sam, you say -1 to 0, and that's nice. That's correct. It's -1 to 0.
Yeah, that makes sense.
Make sense?
Yeah.
Well, you see, look at it. How do I know? Because here I can convert it if I want to this form. I see that it's a construction from -1 and k goes from 1 to n. If you don't right away see it converted to this form, it's again all you're doing. I'm not really just recognizing the form. I'm just saying a construction worker is going to the different rectangles and builds an elevation. I actually imagine sticking a pole to construct the height of the rectangle at the right end point. Okay. is walking to first interval, second interval, third interval. And because those things are very relatable, that's what you do in combinatorics with probability, right? So because this is relatable, you understand right what it is. Okay, next lecture, guys. So
Professor,
much
I
to
do have to go. I will.
All
I
right,
will
all
talk
right.
to you.
Take
Bye,
care.
guys.
Take
Thank
care.
you.
It's too bad you're missing the beginning.
I know. I'm gonna have to watch it. I guess.
Okay.
This is important. I'll talk
All
to
right.
you.
Bye.
Guys.
All right. Oh, screen sharing stopped because I switched. Okay, so let's share it. Here. Are we here, guys? Guys, are you here?
Yes.
Yes, I thought I
No.
lost you.
No.
Good. All right, so here is my next note, right? So, like Pygmalion's Galatea or Rabilov's Golem, the Riemann integral, it takes a life of its own once you define it, right? So what is this thing? This is really a summation of expressions of the form f of x, which f does not necessarily have to be positive as before, times the width. Okay, so f of x might not be positive. So not, for example, if f of x is less than 0, then f of x dx is just the absolute. It's the negative area. Do you see that? If this is negative, if elevation is negative, then I have negative height multiplied by positive width. So f of x dx will represent negative area of the rectangle. By the definition, if I use the same symbol to calculate for functions that dip below the x-axis, like this one, so y equals fx. Now it's a function that's not positive; it dips below the x-axis, and sometimes comes up, right? So where it dips below the x-axis, if I keep the same formula, it's living still. It has a mathematical life of its own. Maybe no longer interpreted as area, but it has a life of its own. So if function is negative, multiply a negative value by width, you get negative area. So f of x dx is like minus absolute value f of x dx minus area. Okay, if you understand this, imagine that I drew this curve before I show it to you. A is the actual area in blue, C is the actual area in blue here, and B is the actual area, right? If I asked you to calculate the integral from AB of f of x dx, tell me what it will be in terms of A, B, and C. The question makes sense? So those are areas, right? So A, B, and C are positive numbers, but I want you to calculate this integral AB of f of x in terms of the letters A, B, and C. What formula will you write to me?
Do you mean like whether or not the equation is like positive or negative, or?
Well, related to area, very simply. A, B, and C are areas. What is the integral? You understand what I said? So this is a summation of f of x, whatever that number, just numbers multiplied by dx, right? So I can use the same construction, but in this case, elevations are negative. So so let's say over this region, f is negative. But let's say if A, B, and C are the areas, what's the integral now?
Okay.
No? So okay, so come on, guys, that's simple.
So could you just add them with like an absolute value
So
for
is
B?
the integral I'm asking about this quantity, right? Is the integral going to be A plus B plus C?
Is A plus absolute value of B plus C?
But the integral does not, you see, you're right away trying to adjust it to the interpretation. It has a life of its own, as I mentioned, right? You created it to calculate area, but now you apply it for area where f is above the x-axis, right? But now it starts dealing with a curve of this form where the curve is not entirely above the x-axis. So what is this guy going to do?
It's going to be negative.
Over here, right?
Yeah.
Yes. So what's the, so it's a, David, yes, it's a minus b plus c, precisely. Right? Because what do you see? You see rectangles that are here, they have a positive elevation. So here, as you construct the rectangles, they will add up to the area. As you construct the rectangles over this region, they will add up to negative b. And as you construct the rectangles here, they will add up to the area, right? So when it dips below the x-axis, it adds up to the negative area. So the integral, which is the sum of all those rectangles, would be a minus b plus c. Make sense?
Yeah, it does.
Good.
At the moment, for now.
Good, right? So okay, just simple imagination. What do I see? You see, you might look you might see a shaded blue region or shaded red region or shaded this region, but I imagine very, very thin, needle thin rectangles, right? Where instead of area, you see, you're accustomed to thinking area positive, but what this is doing is just multiplying this number by the width. Okay, so here when those are multiplied, they correspond to the area of this region, and over here they correspond to negative area, and over here they correspond to positive again. So it's a minus b plus c, as David said, and as we have written over here. Okay, so now we want to understand other properties of the integral, and all of them come from realizing that what we're doing is just adding some numbers of this form multiplied by very small numbers dx. You can think of those as having the same width for this class if you want, but that's not required. So here are some properties. I'm actually going to scroll down. I want you to see why those properties are true. The integral from a to b of a constant is just constant times b minus a. Can you, without me scrolling down, tell me why that might be true? You can use either geometric intuition or a formal definition of what it is as any sort of gn limit as n goes to infinity. Either Rn or left or middle, doesn't matter, right? So any gn, if the function is continuous as n goes to infinity, will be the limit meaning of this expression. Geometric meaning of the expression or anything else. Why is this c times b minus a? Can you tell me?
If it were a graph, it would be just a straight line, right?
Yes, which means?
Which means it's just the x times the y.
Which means, yes, you're telling me how to calculate it, but exactly. But what are you looking at?
You look at the area.
Yes, but of what?
Of underneath the graph.
Yes. You see, when you describe this, here's what I mean. Melissa, not quite. It's not a triangle. It's a constant here, right? So Melissa at least understands what I'm asking. Imagine that you have those Cloverfield movies, and that's what you're describing. It's like the camera is shaking, and you're showing me a finger, maybe an eye, a nostril, but you're not telling me what am I looking at. Okay? Tell me what is this creature. Horizontal, that's already good. It's a horizontal line. And rectangle is now beautiful. Okay, so you understand, guys? What you have to imagine is, again, you give me sometimes calculation or descriptions, but I ask you something very simple. Identify the object. It's like you show me an eye, a nose, a foot. It's like with you're moving with a shaky camera. That's what I imagine when I hear your descriptions. You see, when you imagine those things, then you understand, you know, how you can think about those ideas. Beautiful, right? So you're correct, and David, you're correct, but describe it. So this is just the area of a rectangle. Wonderful. So then we have the additive and subtractive property. I put them together of the rectangle. You have the constant that you can factor out, and you have the integral from a to a of f of x is 0. Okay, and all the others that we have here. Okay, so this is what we look at. You understand? y is constant, of course, I drew it as positive here, right? It's constant. The area is then the width times the height. I don't need to carry out the subdivision. So I can right away tell what's the answer to it, okay? Even if c is negative, there's no problem, right? I mean, I always have, this is a good weapon, right? I always, when I think of the integral formally, I just think right away, this is what a computer will think of it, okay? If I were a computer, as what Alexander likes computers, right? So if I were a computer, I do not understand anything, but I just go through the formalism. I just say, okay, divide into n parts, take the limit. So I think maybe of Rn, or in general of Gn, right? So you can think of Ln, Mn, or any general, right, construction. For computers, it's nice to maybe use very, very methodical. So Rn or Ln, right, or Mn, right, whatever you like. So that would be a summation from K1 of C times B minus A divided by N. And then this, I mean, it's just, there is no dependency on K. So this is this number multiplied by N. So you get this, okay? Now, why is the sum of the integrals the integral of the sum? That's also pretty obvious. If you remember that this is just a summation, I have a rectangle with this altitude times dx. But I can distribute the dx to g and to f. You understand? This is just the width. So if distributing, I now have one rectangle with f and one rectangle with g, which I can sum separately. You understand? It's really a summation. Even though you take limits and you make it slightly more complicated, what it is really is just summing a bunch of rectangles. Right? It's something much simpler than it appears. So that's why I right away would have known that the sum of f and g at their integration is the integral of first plus integral of second. Okay, and here is trying to explain that formally. Right? So formally, this is not a finite sum; it's a limit. So what I do is limit as n goes to infinity, and this is a Gn representation, a generic representation fxk plus gxk, delta xn is the thickness of the interval. So here I distribute the delta xn, and I get, and then because it's a finite sum, I can add the f sum part and the g sum second, and take the limits of this part and the limit of that part separately, because limit of the sum is sum of limits. You understand? This is, of course, writing more, but really, I can very quickly in my head kind of go through roughly what it is. It's a sum that I can add the f's first and then the g's, and then have the solution. Good? You understand why this is obvious, right? This is a property that if you were studying this integral and nobody was explaining to you, you could have discovered it, right? The notation is extremely suggestive. You could have discovered this property. You would have known it to be true. Same goes for f minus g, because it's really just a property of summation that allows it to distribute. Another very obvious property is that you can factor out the constant. Why can you factor out the constant? Because it's just an algebraic property. Constant times the sum is you can distribute the constant in or out, right? So this part, c times the integral, it's like c times the sum. Whereas this part is where the c was distributed to each term of the sum. So that's why you can factor a constant. In other words, what is this really? It's not some more complicated calculus problem. It's the distributive law, right? It's the idea that you can factor a number out of addition and put it into it, right? So it's something that you have done many times, and you can establish that by limits if you have to kind of argue rigorously, because this is a limit of the sum, and you might worry about what happens to a sum when you increase the number of terms or not. But this is pretty clear, right? Now, next question before I move on, guys. Why is this 0? Could you explain to me why integral from a to a of f of x dx 0? A minus a. David, please be more specific. A minus a is 0, yes, but I don't see just a and a. I see this expression. More specifically, why?
Because you're not finding what you're looking for is 0. I don't know how to explain it.
Well, that's a problem. Explain to me so that I understand. When people say so, it's the same. Well, you see, it's a very bad word. What is it? If you begin summing from 0 to 0, there is no area in the space. Okay, I like Alexa's, and Batel says one line. I also like that. Okay, same place. So I would have said this. Okay, I see that I'm looking at a city that has no room. It's a terrible Manhattan that has only one point at A, and there is no thickness. So there is only elevation multiplied by 0 thickness, so area is 0. So my skyscraper is, it has 1 dimension, not 2 dimensions, right? So that's in terms of, exactly, that's very good. So you see, 0 because we have this geometric idea, and I can do it by Riemann sum, right? Because what do I do when what I do is I take the top point, so I begin with this point A plus k, top point minus bottom point divided by n, and the width is a minus a divided by n. So this is what a computer, I think, understands this. A computer doesn't understand, but if you ask a computer to verify that 0, the computer will try to possibly take this limit, or you know, an approximation of it. So what happens here is that I don't displace anywhere, because for every k, as k goes from 1 to n, it's f of a. So what happens is I take f of a times the width, which is 0. So I add up n times f of a to itself, but because I multiply each by 0, it's like I added n times 0 to itself. You understand? So a computer, if you do this procedure, let's say for n going to infinity, that means n is, let's say, 1,000,000. The computer will add 0 to itself 1,000,000 times. Okay, and then billion times, doesn't matter. You add 0 to itself, nothing happens. Now the next question, guys, the hardest one possibly here, what happens if I switch the sign? So instead of having a on the bottom and b on the top, they reverse. What's the relationship between one and the other? So for example, what happens if I start at b and go to a of f of x dx, and then y, right? So in terms of the previous expression, right? So dA f of x dx, how is it related to AB f of x dx? Question understood? So here is where those summations are pretty useful, right? So formally, I like the formal definition, right? So I think of it, I don't try to right away come up with geometric interpretations. I understand this expression as taking limit as it goes to infinity. And what do? My process is it's like what a lot of students that don't understand the subject, they think actually pseudo formally, because they want a rule, they want a procedure. So a computer will follow this procedure. Take this number on the top, subtract from it the number on the bottom, divide by n, right? That creates the delta xn, correct? So it doesn't matter if this is smaller or larger, just whatever is on the top, subtract what's on the bottom, and I get this. I get the interval width, so to speak. And then I begin displacing from, let's say, this point, all the way until k starts from 1 to n. So I get this summation. Do you agree? So guys, hopefully you are with me still. All right, so why is this b? Because I start from this point, I get f at the bottom point plus k times this difference divided by n times this difference divided by n. And then I try to recognize what is this thing. Look at it. Oh, a minus b, let's say a is smaller than b, right? Let's say a is 1 and b is 2. So if a is smaller than b, this is the negative interval. So I can make it a positive interval by factoring a minus 1 and putting it over here, right? So it's b minus k, b minus a over n. And here, I also can factor a negative, and I can move the negative, factor it out of the sum. I put it over here. You follow? And then I look at this expression. What is that? I already, unfortunately, told you, right? Do you remember? You see, we did it in the previous lecture. What is this expression? Without the minus, it's just the expression for the left-hand rule for f. You see, but where we start, like some started liking to start at the right, at b. So I move from b to the left, or when k is equal to n, I will get to the point a. Okay? So this is just ln. Do you see that, guys? I read it and I see, okay, so what's the construction? Once I factor the negative, once I apply this formalism and I factor out the negative, this summation without the negative, it's just the left-hand rule for the function f. So that means it's minus integral from a to b of f of x dx. You understand, guys, right? It's going to be important for the fundamental theorem of calculus. You see how nobody had to teach you this rule. If you understood this formalism, this pattern recognition, you would have come up with this formula. You just begin with a right-hand rule for this function, and you add up with minus the left-hand rule for this integral. So because all those rules produce the same limit, you get minus the integral. Okay? And another property is if I go from a to b, I can pause in a point C between A and B, and the integral from A to B is the integral from A to C and then from C to B. Why is that true? Because of this picture, you might say, right? But what's better is that C does not have to be between A and B. You understand? This picture is makes it clear why that would be true if C is between A and B. But what happens if C is below A? And is this still true? Is it true that A to C, then C to B is just from A to B? And the answer is yes, it is true. Yeah. C does not have to be here or here. It will be true regardless. You see, and how is this? Let's calculate, right? So here I assume C is on the left. It's over here. It makes sense, but L and everybody else, that if C is between, then you can break it apart because it's like cutting the area, right? So intuitively, it's clear, right? Or if you don't need to think of area if the curve is dipping below the x-axis, just think of the formal sum, right? It's just a property of the sum from here to here, and then from here to here. But look what happens. Suppose C is to the left of A. So, right, so what happens? So then the integral from A to C and then from C to B can be written as follows. So it can be written as so this part, look at it, this part can be written as minus the integral from C to A. Do you agree? Because I want the smaller number to be the leftmost number to be bottom and the right number to be on the top. So by the previous property, I can convert this into minus C to A f of x dx. That's by what we verified above there. Yes? So it's minus from C to A. And then this part I can break. Look at it. C to B. C is to the left of A. So I can break it C to A and then A to B. Right? So it's this. And then this, the middle guy I break into C to A to B. And look at it. C to A with a minus. So this cancels out and I get AB f of x. Do you understand me, guys? I just follow this pattern, right? This summation, I convert it because it's from A to B. It's in the wrong order. I put minus and I put it in the right order. I can always flip over, right? I can always flip over based on this result. Okay, it doesn't matter which is above, which is below. If I want to flip the order, if I want A to be on the top and C on the bottom, I just multiply by -1. So we have this, right? And we put minus here, C to A. And then everything cancels out. And also if C is on the rightmost point, what I can take A to C, C to B, and I see it will be from A to B. Wow, because it will be what? If it's the rightmost point, I can put this as A to B, and then B to C. So the first part I can break from A to B, and then from B to C. Right? And then this part is the same as minus B to C. If I switch their order, it's minus. So those cross out, and again I get AB f of x dx. So it doesn't matter where C is. It could be here or anywhere else. This property is true all the time because we checked already all possibilities: middle, to the left, and to the right. So for any C, it's very convenient for what will come. Okay. So next, guys, here is the next challenge. Okay. So here you have 3 integrals. I want you to evaluate them as quickly as you possibly can. Forget about one rule or another. Your goal is to right away, as quickly as you can, find the answer. Can you do that? I'll be back as you think. All right, so let's see how we do that. Okay, so you see, one thing is, what are you looking at? What is this thing that you're looking at? Always ask yourself that question. So what we're looking at, look at it. Set y equal to root 1 minus x squared. If I square and rearrange, I see x squared plus y squared equal to 1. So I'm looking at part of the circle. Now, because the circle is, by the way, of radius 1 and centered at 0. And now notice that it's the right wing of that circle and its upper part. So this is just 1/4 of the circle. So right away, I see that the area is 1/4 pi. Good. What about this thing, guys? B. What are you looking at? What are you integrating? Always think about the shape, or you can do other parts. Right? You don't have to think of it as one shape. You can decide what to do here, right? Straight line, yes, that's good, right? It's a straight line. You can also, but you see, so but straight line is the skyline, so to speak. What geometric shapes are we getting then? Well, let me show you. No, you want to do it? Or what you? Okay.
I don't know.
Fine. Look at it. First of all, I can use properties. My goal is what? Triangle is good, Sam, right? My goal is to do it as fast as possible. So I break it into one part, another part. And what is this part? Triangle. What is this part? Negative rectangle, right? So that's the way I would have thought of it, right? So I see, and I colored red, meaning below the x-axis, and blue above the x-axis, right? So look at it. X from 0 to 3, that means a right triangle of base width 3 and height 3. So that would be 3 times 3 divided by 2, or 9/2 is this part. And this is -1 multiplied by width 3. So it's -3. So I have 9/2 minus 3, which is 3/2. Good? You see what I'm saying, right? So it helps sometimes, not always. Those are usually for a complicated integrals. The shape is complicated, so I don't know the area. So it's not profitable to do anything else here, right? You just to right away see this area minus this area, so it's 3/2. It's very fast, right? What about C? Can you try to figure out how to solve C? As quickly as you can again, right? All right, so you look at it, and the question is, what do you see? See, interval is from -3 to 3, this expression, etc. Right? So what shapes do you see, guys?
And down something.
What? Louder?
Up and down something.
Well, up and down is when you lose consciousness. What do you see?
I don't know. I'm super lost. I don't know.
No, come. Why lost, right? So look at this thing, just those shapes outlined, right? So you see, what do you see here? Look at it. I just moved it very fast, and I'm sure many of you can tell me what you see there. What was that? No? All right, so all right, so here is what we see. Oh, look at it. First part is y equals to 9 minus x squared. So if you rearrange it, it's y squared plus x squared equal to 9. And because it's from -3 to 3 and there is a positive sign, this is half of a circle of radius 3. So it's 9 pi over 2 is the area of this shape. Second part, it's x, integral of x from -3 to 3. And from -3 to 3, look at it. For this x, you see two triangles, one negative area, one positive area. They're the same shape. They cancel each other to 0. So this middle guy is 0. In fact, integration of any odd function from a balanced interval around 0 will be 0 because one part cancels the other. And here I see a rectangle. So I see I see half of a circle. I see two triangles like a bow tie. And then this, right? Of course, because I show this picture, right? It's like imagine something very pleasant, like well, actually I never went to a kindergarten, but imagine you go to a kindergarten and they say Avi Ron, right? Or they say something, right? So you to train your recognition, airplane, right? All right. So the answer then is this number plus 12. So this thing, okay? Here is another example, guys, before. So let's do this one. And then I suppose we can call it a day. I don't know if we could. So what is, we don't know the function, but we know that integral from 0 to 10 is 17, and the integral from 0 to 8 is 12. What's the integral from 8 to 10, please? Beautiful, but wonderful, right? Very simple, right? It's just the full area from 0 to 10 minus the area from 0 to 8 is 17 minus 12, and it's 5. Wonderful, isn't it nice? And then there are comparison properties of the integral, which we will possibly talk a little bit about. They're obvious. And then something, hopefully, that you begin to see that it's rather cool. So how do you figure out all sorts of complicated areas, right? So for pyramid and for the cone, remember we had cone some time ago, and I gave you the formula. So here, with those ideas, you can very quickly establish those formulas, right? You would know what they are. All right, so that might come up next. So I don't know. I guess I'll pause the lecture at this moment, right? Since I think a lot of you are aching to leave me. But guys, whatever you think, just budget your time. It's very dangerously close to the final. I would not be surprised if it happens on, I would imagine, Monday after reading day. Hopefully they give you reading day, right? I'm not sure Monday, I'm just saying. I have no idea when it is. But
to, yeah.
Yes, do you know when it is? I still do not know. Huh?
Why Monday?
No, I didn't say Monday. I just imagine, right?
And
I
if
think
if the final is overlap with another final, what I do then?
Alexandra, take care. Sorry, right? Sorry, but I'm gonna pause the stop recording.